Let's start the video. In this video, I'm going to discuss 6 questions and the solution for those questions. So I request all of you to pause the video first and find out the answer for yourself and then continue the video because I'm going to discuss the solution for each of these questions. Let's discuss the first question. The correct order of stability of the following carbocations. So we have been given 3 carbocations and we have to find out the order of stability. Let's see the nature of the carbocation. This is a tertiary carbocation. This is a secondary carbocation and also it's allyl secondary carbocation. This is a secondary carbocation, but it is attached to a methoxy group. We already know the secondary allyl carbocation and secondary methoxy carbocation will be more stable compared to a tertiary carbocation. We should also know that this MEO will not do any resonance stabilization here. Instead, it can only have inductive effect on this carbocation, makes this the least stable among the three. Now, to find out between this and this, what we have to do, even though you can say this is a tertiary carbocation, the number of conjugate resonance structure, hyperconjugation structure for this and this will be the same. So the only difference between this and this should come from the stabilization by MEO or the stabilization by the double bond. The stabilization by MEO will be better than the stabilization by the allyl because of the resonance here. Even though we also have resonance here, but in both resonance structure the octet is not complete, and also we have a minus I effect of MEO in this compound. So the correct answer is D. Let's look at this question. According to Ben's rule for p block elements, the correct combination of the geometry of the central atom and the position of more electronegative substituent is. Ben's rule mostly applicable, will be useful in predicting the structure of trigonal bipyramidal structure, and in that the more electronegative substituent will also prefer the axial site. So the answer is A. This is also straightforward. We already know the dipole moment depends on bond distance as well as the electronegativity difference. But among the three, we don't have to worry about the bond distance, just have to find out the electronegativity difference. So the answer should be C. So NF3 is will have the least dipole moment because it will have small bond distance as well. At the same time, the electronegativity difference will also be small. So answer C is so straightforward. Between H2 and NH3, it's not that easy to predict, but by way of elimination, we can predict C is the answer. Now let's discuss this question. Among the structures given below, the most stable conformation for the following compound is. When you have 1 to cis, we already know one has to be equatorial and the other has to be axial. And the same is true for 1,4 as well. 1,4 cis means one has to be equatorial and the other has to be axial. Now, between these two, which one we want to have equatorial, which one we want to have axial? Let's say this is axial, this is equatorial. If that is the case, if this is equatorial, this is axial, by 1,4 relation, this is also axial. So which means having this equatorial and this axial will also make this also as axial. We don't want that. Let's make this axial and this is equatorial. In that case, this will be axial, which means this will be equatorial and this will also be equatorial. So the correct answer is C. Let's come to the fifth question. This is basically a nucleophilic substitution. So is that if it is a electron withdrawing group or minus R group will favor the reaction and will increase the rate constant. So we are looking for the order of minus R group or minus I group. It's so straightforward. The answer is A. Because OCH3 will have plus or effect. We don't want that. So the answer is A. Because even though OCH3 is minus I, but it is plus R in this case. The last question, the simplest of all, we already have a enantiomeric pure compound, cyclohexene 2-ol. We're going to do an epoxidation. We found that the 95.5 mixture of A and B. When we have already chiral center present in the molecule and it is enantiomeric pure, when we do a when you introduce a one more chiral center, the product will be diastereomer, because let's say the initial product is R. The final product, when you introduce a new chiral center, the final product have two combination, RS and RR. Apparently the relationship between the two will be diastereomers, right? So the answer is B.